This is May-June 2023, P42. Let's try to solve this question of this paper. It says states Newton's law of gravitation. So what you simply have to suggest it is that the force of attraction between the massive objects is proportional to the product of masses, which is m1 multiplied by m2. In the book, you will see it sometimes as written down as mm, large m multiplied by small m. And the second point is that it is inversely proportional to the square of separation between them. So you just have to mention these 2 points in English. You can check the marking scheme for the correct answer as well. He says that there is satellite, orbit R, radius of orbit, this is important, okay? And the period is t. The planet is a uniform sphere. Use Newton's law of gravitation to suggest that there is a relationship that looks like this. This is a very common question that's going to, reappear again and again. So first we need to suggest the logic where we start the question from. So we know that gravitational attraction or gravity provides the necessary centripetal force. You have to write this down in English, okay? So we know that the gravitational force is actually Gmm over r squared. And we know that the centripetal force, since we are relating it with time t, is equal to mr omega square. You see, we do have mv squared over r, but the problem is that the v does not open up to any function of time. But we know that omega is equal to 2 pi f, or it can be written down as 2 pi by t. So we know that this exists. That's why we're using omega square's equation. So simply right off the bat, we can see that the small n cancels out. The r squared goes to the other side and becomes r cubed. So we can locate at least one r cube in the equation. It looks like that we're going this in the right direction. Okay. So we have G capital M equals to r cube into the bracket of 2 pi by t whole square. Let's take t on the other side. So this becomes Gm but with t square equals to r cube but with 4 pi square. So we have successfully made it look like the equation that he wants us to show. Usually these parts are just for the sake of understanding that if you are unable to solve this, you can use this relationship for any incoming parts that are going to follow this part. So even if you're unable to solve this, please do not forget to solve the next parts. He says the Earth may be considered, okay, uniform sphere of mass this, radius of this. A geostationary orbit is around the Earth, okay? The expression in B to determine the height of the satellite above. Now, this is what you might miss out on. Above the surface of the Earth, whatever radius is, whatever distances we've been considering for now, have been from the center of Earth to that respective point. You see, if this is the surface of the Earth, and this is, let's say, the radius of Earth to be 6.37 into 10 raised to the power 6 meters, as given in the question. And he says that the radius of orbit is not given. We are going to find that out, okay? That would be from the center of Earth up to the satellite, wherever that satellite exists. What he's asking in the question is actually from the satellite up to the Earth's surface. So what you're going to find from the equation is actually going to be this r, from the center of the Earth to that respective orbit. So just be careful about that. So what we have is t squared gm equals to 4 pi square into r cube. We want to find r cube. So let's replace every value. So the time period is going to be, of course, since it's a geostationary orbit, it will be following the 24-hour period cycle. The G value is 6.67 into 10 raised to the power minus 11. The mass of Earth is given to us as 5.98 power 24. So 5.98 into 10 raised to the power 24 divided by this 4 pi square will go to the other side in the division. So this is going to be 4 pi square, and then this whole of this will be actually the cube root because we are finding the r cube. So when you're successfully done with this as r cube, or after taking the cube root, of course, after taking the cube root, you will get an answer of 4.22 into 10 raised to the power 7 meters. Remember, this is from the center of the Earth up to this point. We are only required to find above the surface of the Earth. So I should subtract this radius from this value of r to get this height x. So minus 6.37 into 10 raised to the power 6. We got x is equal to 3.58 into 10 raised to the power 7, which up to two significant figures becomes 3.6 into 10 raised to the power 7 meters. I hope that we understand this idea. Okay, moving on to part D. it says that another satellite circle orbit around the Earth, same orbital radius, speed in satellite C. Calculate the angular speed of this orbit, give the units of no problem in that. If it has the same orbital radius, if it has the same period, we can use the formula omega equals to 2 pi by t, since this is the angular speed formula. So that would be 2 pi divided by 24 hours into 3600, converted into seconds, of course. This comes out as 7.27 into 10 to the power minus 5 radians per second. So this would be 7.3 into 10 to the power minus 5 unit radians per second. He says despite the same orbital period, the orbit of the stationary satellite is not geostationary. So just two ways in which the orbit could be different from the orbit of satellite in C. No problem. The orbit could actually be around the poles. You see, if this is the Earth, let's say this is the north and this is the south and this is the equator, for example. For geostationary, it has to be along this line generally so that it can have the same 24-hour period as the Earth. Okay. It's possible that the satellite is actually rotating like this in unison with the Earth, right? So the first difference could be that it's an orbit, or it is in orbit around the poles, or something like this, but closer to the poles, or like this, around the poles or close to the poles. Okay. The second thing would be that if we look at the orbit, it's generally from east to west. The Earth should be rotating like this, or the satellite should also be following this rotation. It is possible that this satellite is actually moving in the opposite direction. So it is opposite to east and west direction or orientation. All right. Question number 2, state what is meant by an ideal gas. Now this is a very repeated and common question. Whenever he asks you this question, you should say that a gas that obeys the ideal gas equation, which is PV equals to nRT. And then you go on explaining everything in English, what's P, V, and R and T. So P would be the pressure, V is the volume in meter cube, N are the number of moles, R is the universal gas constant, of course having a value of 8.31, and T is important. You don't say T is temperature, you will have to say T is the thermodynamic temperature. This is different from simple temperature because this assumes that you are talking about the Kelvin scale, right? So that's why we have to mention this in this way. He says, what's the temperature in absolute zero? So we know that it's minus 273.15 because we have that equation, that 273.15 plus degree centigrade gives you the answer of Kelvin. So if degree centigrade becomes 0, then of course, or absolute 0, that would be a Kelvin 0. So what would be the temperature or in degree centigrade? That would have to come over this side to become negative. A sealed vessel has a mass is given, temperature is given, but notice it's in degree centigrade. The pressure is given, the volume is given. Calculate the number of molecules. So first we calculate the number of moles and then we can go towards the number of atoms by using Avogadro's constant. So simply use PV equals to nRT. The pressure is given to us as 1.37 into 10 to the power 5. Volume is 0.640 as over here. Make sure it's in meter cube. Equals to number of moles, which is what we have to calculate. The gas constant is 8.31. The temperature will be 227 plus 273.15. The number of moles that you're going to get out of this is going to be 21.095 moles multiplied by Avogadro's number, which is 6.02 into 10 to the power 23. We get the total number of atoms, capital N, equals to 1.27 into 10 to the power 25 atoms. Okay. So this will be 1.27 into 10 to the power 25. The mass of one molecule of the gas, very easy. He says that the total mass of the gas is 0.0424. So total mass 0.0424. It's in kilograms. Okay, fine. So this will be in kg. Divided by how many number of people, how many number of atoms are participating this to constitute to this mass. So that will be 1.27 into 10 to the power 25. So this comes out as a very small number, which is 3.34 into 10 raised to the power minus 27 kg. So each atom inside the sample has a mass this much. The RMS speed of the gas. So we do have an equation in which we say that the kinetic energy, the standard equation, that the kinetic energy is equal to 3/2 kT. This is also one of the proofs that is common for this chapter. So I know that the kinetic energy is equal to half mc square equals to 3/2 kT. What is the beauty of this equation? It's that this part, the left hand side, is only for one atom, but this part is for the whole system. So what does this tell me? If I know the information about one atom, I can predict the information about the whole system. So that's what he's trying to do with us. He has told us the temperature of the whole system. Now he wants to know what the average speed of one molecule may look like to us. And we also know the mass of one atom as well, which is going to be participant of this side of the equation. So this will be 1/2 into mass, which is 3.34 you found in previous part, minus 27 into RMS speed square equals to 3/2. K is the universal, I think this is the Boltzmann constant, yes. So 1.38 into 10 raised to the power minus 23 into temperature would be 500 Kelvin. Of course, we have added 227 with 273 again. So when you find out the speed, of course, by taking the under root on the other side after performing the correct algebra, you'll find out the speed to be 2490 meters per second. So this answer comes out as 2490. So just by looking at one atom, I can predict the condition of the rest of the system as well in terms of temperature. Then he moves on to this graph. This is new in terms of simple graphical analysis. By this time, what we have done is we are familiar with the direct proportionality graph, what it looks like. It passes from the origin and is a straight line. We also know that y is equal to mx plus c may look like with a false origin, with the plus c and with the minus c. We are also familiar with that. We also know that y is proportional to x square is going to look like a parabolic equation like this one, ever rising, ever increasing. We also know that y inversely proportional to x is going to look like a decaying curve or exponentially decaying curve like this one. So these are the graphs that we are familiar with. This is going to be something new that you might have not tried before, but of course, mathematically speaking, we should be familiar with this. Is comparing RMS speed with temperature. So we go back to the formula that we used for the previous part. Of course, by this time, he knows that you know the formula. So half mv square is equal to 3/2 kT. Now we understand that rest of everything is actually the constant. What we are left with is a v square relationship with t. Now when you take the square over the other side, this becomes v proportional to under root of t. Right? This equation looks like y proportional to under root of x. How have we drawn this conclusion? Because on the y-axis we have the RMS speed, so that's represented over here. And on the x-axis we have the temperature, so that's represented over here. Now for this graph, even if you use a mathematical calculator, or even if you use a simple O-levels method that you've already understood to make these graphs, you will notice that this graph is going to come out like this. So this is the v. Obviously, he has not mentioned the speed over here. What's the speed going to be? Because this is what you were required to find out in the previous part, right? So we will not mention it over here. Otherwise, if he had not mentioned this, if he had left this as an empty space and he wanted us to mention the values, then of course we would have mentioned over here as 2040, 2490. But anyways, moving on. So what is this graph going to look like? This graph is going to look something like this. Previously or initially, the graph will have an increasing or a high gradient, but eventually the graph will start reducing its gradient. And believe me, this is not a problem of physics. This is just how this mathematical equation actually draws out to be. So if you have memorized all of the systems before, just add one more system in your equation or in the list of common questions, is that y proportional to under root x actually looks like this, Okay, so be careful about this. All right, moving on to question number 3. This is the question that actually creates trouble for everyone. The first law of thermodynamics, because sometimes it makes sense, sometimes it does not make sense. But let's try to make it easy for us. Before we start with this, I would like to give you a small summary of what we have done in my lectures of internal energy. To keep it simple, we have Q plus W. Now, internal energy is calculated at the end. First, we have to tell what's happening with Q, what's happening with W. So if you are, for example, if you are heating it up, Q will be positive. If you're cooling it down, Q will be negative. And similarly, for work done, which is P delta V, if you're compressing the gas, or if the gas has been compressed by the external force, this W will be positive. And if the gas has expanded by any means necessary, for example, if you allowed it to expand, or if it has expanded, then the W will be negative. And the logic for this is that if the gas has to expand, it will take the energy budget from the system and then try to do work against the external pressure to actually eventually expand. Similar thing happens with the compression as well. If the gas is compressing, that means some external force is doing work on it, and it is making sure that that energy stays inside the system due to the compression, because when you compress it, the momentum changes of the molecule, and of course that energy translates into some form of kinetic energy, or that translates into the internal energy. So this is a small general guide that we have already studied in my lesson, that's already recorded and uploaded. We will use this guide and a few other ideas to solve the question that is ahead of us. First, let's see what he says, law of thermodynamics. This is what I've just explained to you. But just one exception, that if you're mentioning this as delta U is equal to Q plus W, that means that you've taken both of them to be positive. So just make sure that you explain this as thermal energy added. Simply say thermal energy added, because that's what you're doing. You're heating it up. And for this, simply say that this is work done on the gas. So this compression is on the gas and expansion is by the gas. Okay, simply on and by changes the sign of the system. To get around this problem, I've told you what's actually on the system, what's actually by the system. Anyways, so the state of an ideal gas is continuously changing. Okay, fine. He says that the cycle is ABCDA. So what does that mean? It means that if the starting point and the ending point are same, that means after reaching this point, the total change in internal energy will be 0. So neither it's going to have some internal energy, or neither it's going to lose some internal energy. Whatever it would have at the beginning, for example, if it had 500 joules of internal energy, for the sake of example, after completing the whole cycle, it will still have 500 joules. So this is basically the idea used for the working fluid in any system that is operating with the help of a gas. You add energy into the gas, ask the gas to do something for you, and then you remove that energy back in another format, right? And then you get the gas back at the same state where you started from. It's like a working fluid. It's like a working fluid for car engines, for hydraulic systems. So you are adding energy to ask it to do something else. But anyways, let's go ahead. So this is the system that is given to us. Let me make some space for this by removing this. Okay. So we have the equation as delta U is equal to work done on the gas, which is going to be represented as W, which in short is actually P delta V. We know this, right? Plus Q, which was heating. Now in this question, heating is not mentioned in any situation, but we will try to predict it, whether it's happening or not. Okay, let's see. So first he says what's happening from A to B. What will happen from A to B? Let's start from this side, because delta U will be figured out later. First we have to start with W and Q. What's happening with W and Q? But let's see what's happening. So as we're moving from A to B, this is volume V2, for example, and this is volume V1. I can see that there is compression taking place, and we understand that if it is compression, the work done will be positive. So I can very well say that this work done, P delta V, in this case would have been positive, because the gas is being compressed. So the gas is being compressed. Okay, fine. Now, how do you make sense of this delta U? We don't know the information about heating and cooling. We don't know what's actually happening. But let's try to go back to this graph and see that this is actually P1. And let's say this is actually P2. So while this was happening, the pressure was not changing. The pressure was constant. Let's try to use the equation of ideal gas, because we are assuming that this is behaving like an ideal gas. PV equals to nRT will be applicable. So for A to B, let's try to make some sense in this by using that equation. So we have PV equals to nRT. Now we understand that there is no gas escaping. The molecules are still the same. So the number of moles, the number of atoms inside the gas will remain constant. The universal gas constant is itself a constant, so no need to discuss about it. So, and we also realize that the pressure is constant, because even at this volume V2, the pressure is V1. At volume V1, the pressure is P1. The pressure is not changing. So all the things that I've highlighted with blue are actually a constant, right? So we are left with only an equation that goes something like this: volume proportional to temperature. Now, my logic or the thinking process, please be careful about this. How are we looking at this? How are we thinking about this? Since I can observe that the volume is decreasing from V2 to V1, since the volume is decreasing, I can only predict, I can only imagine that this has been done because the temperature is decreasing. The temperature is decreasing, right? Now, since the temperature is decreasing, we go back to the first law of thermodynamics, which is delta U, sorry, not this one, the simpler understanding of this, which was internal energy was actually the sum of kinetic energy plus the potential energy. Now, for ideal gases, we already know 100% that the potential energy is actually equal to 0. Why the potential energy is 0? Because there are no number of bonds. The bonds do not exist. And if you want to go a bit deeper for this concept, this is what potential energy graph looks like between any two gaseous atoms if they were not ideal gases. The potential energy between them actually goes something like this. This is molecule number 1, this is molecule number 2. If you, of course, bring them close together, the potential energy becomes less negative, and we say that it is increasing. But if you take it away, or if you stop thinking about it, you can read about this in the book in great detail, but since it is going to be 0 because of an ideal gas, we are not discussing about it over here. We've understood that internal energy depends on the kinetic energy. We understand this topic, we understand this point. And we've also established that the temperature is decreasing because I can observe that the volume is decreasing. If the temperature is decreasing, that means that the kinetic energy is decreasing, because we understand from kinetic model of matter that the kinetic energy of any system is actually equal to 3/2 kT. This is actually what we did in the previous question as well. Over here, this is what we've been doing over here as well. So we already know this information, okay? We just have to piece it together like a puzzle. But anyways, let's see what's happening. So if I know that the temperature is decreasing, kinetic energy must be decreasing. This is where we've drawn this conclusion. So now I know that the internal energy must also be decreasing. So over here, we select internal energy to be decreases or decreasing. And if there had been an extra column on this side, for example, for Q or heating, most definitely for this case, it would have been a negative Q. And overall, speaking in terms of energy exchange, at least in terms of energy exchange, what would have happened to make more sense of the situation is that you have actually cooled down the system from an external force, either by refrigerating it, either by removing any thermal energy from it. You have cooled it down. As a result of that, as a result of cooling effect, the gas also got compressed, or it actually shrunk, and as a result, since some of that energy has to translate into work done due to compression, and some of it still remains inside the gas as a decrease in internal energy. So what might have happened is that, for example, you provided a cooling of 1000 joules, you allowed the gas to get compressed, so 500 joules might have been used for compression, and still minus 5000 joules are still present inside the gas as a change of internal energy in comparison to previous and the current situation. So still the change in internal energy, or delta U, still shows a sign of decrease. Why? Because at this point when you come back, your delta U should have been 0. So at this point the U would have been minus 500 joules based on the values that I've taken for this example to understand. Okay, so what this example tells us, that the cooling has overtaken, it was more dominant, that it not only compressed the gas, but it also caused the internal energy to decrease much more. So I hope that we understand the logic behind this. In some examples, in some videos, you will see that they have tried to justify it with potential energy. For an ideal gas, the potential energy does not exist. So that logic does give you the correct answer of decreasing, but it is not applicable over here because we know that the potential energy does not exist. But anyways, you can also use that to justify this answer as well, if that makes more sense to you. Anyways, let's move to B to C. So what's happening from B to C? From B to C, I see that the volume is not changing. So the work done, which is this part, in this we have P delta V. If the volume is not changing, but the pressure is changing, that means that at least this part of the equation is going to be 0, because delta V is equal to 0. So P delta V is going to be 0. So whatever is happening in this situation is purely because of temperature. Now for B to C, let's employ this second law equation again. The PV equals to nRT, ideal gas equation again, PV equals to nRT. Now we understand that the volume is constant, this is constant, nR is constant. So the equation that is actually applicable over here is going to be pressure being proportional to temperature. This is what actually happens with when you're cooking in a pressure cooker. When you've enclosed the container, the volume does not change, but as you're providing more heat and you keep on adding thermal energy, you keep on providing thermal energy into the system, you see that the pressure starts rising, the pressure starts increasing inside the pressure cooker, right? So this is just a real life example that I've associated with it. So if you increase the temperature, the pressure increases, okay? So we understand that. Now, if we go back to the first law of thermodynamics, which is delta U equals to Q plus W, we've established that this is actually equal to 0 because the delta V is equal to 0. So P delta V becomes 0. So the whole internal energy, the delta U, has come down to heating only. And we've understood that this temperature is a representative kinetic energy. And we also understand that this Q is actually representative of heating and cooling, representative of that. So we understand that if this is increasing, for example, the temperature must have been increased so that the pressure appears to be increasing. We didn't do it from the outside by changing volume. It has happened because we provided heat to it. When we provided heat to it and we did not allow the volume to change, ultimately the pressure will start increasing like a pressure cooker. So if the heat has been provided, the internal energy would have increased in this situation. So simply put over here, the internal energy increases. Why? Because pressure became proportional to temperature. If you increase temperature, you increase pressure. And of course, if it had the complete Q table over here, this Q would have been plus Q. Because now you have added energy into the system and it did not translate into changing volume. It translated purely into increasing its pressure by increasing its temperature. And how did you increase the temperature? You increase the temperature by providing heat. So that was plus Q. So if by a common man's understanding, this will be heating and this will be cooling. I hope that we understand this question in terms of very simple mathematics and very simple logics. Okay, he says use first law of thermodynamics. Again, he is bounding us to use this delta U equals to Q plus W to describe the energy transfers associated with the one complete cycle. Now to discuss this, we need to go through this complete cycle. So when you go through this complete cycle, let's say that the delta U going from A, B, C, D, and then back to A, it should have been 0. This is what we established at the beginning of the question. Now, this delta U also depends on the Q plus W, right? Now, what we realize, if going back to the system, what we realize that while moving from C to B, while moving from A to B, this cycle, when you were moving in this direction, you had done some work, of course, by P delta V, right? So let's call this work done in sector AB as P delta V, no problem. And when we go back to this P2 C to D, we realize that when we move from C to D, we're doing something opposite to what we've done from A to B, but there is a difference. The difference is that P1 is a smaller value and P2 is a higher value. Let's say that this is 500 and let's say this is 100. Now, although this V1 to V2, the delta V is still the same in terms of values. The change is same, but this change is happening at a much higher pressure. So I can see that the work done in C to D equals to P delta V. Let's call this P2 and let's call this P1. These are two work done, but what can I say about their relative magnitudes? Which one would have been greater? So I realized that this CD work done would have been greater than work done AB. So work done in C to D is greater than work done in A to B, simply because in P delta V and P1 delta V, although delta V is exactly the same in both situations, the change in volume is same. But since pressure 2 is greater than pressure 1, the work done in that section is greater than the other section because it is happening at a higher pressure, right? Now, since you are allowing this gas to expand in this situation, this would have been an extraction of energy as minus W. Over here, you allowed the gas to compress. So this was a plus W situation, as explained in this shortcut. You allow the gas to compress, this will be plus, expand, it will be minus. But I can see that addition of energy has been less, but extraction of energy has been higher. And when you come back to this cycle, we realize that on the extreme edges, we have not done any work. For example, over here, the work done was 0, and over here, the work done was also 0, right? So what are we left with now? What is actually happening? We have actually extracted more energy, or you can say, you might have been extracting, let's say, 800 joules of compression or expansion, and you're only giving back, let's say, 300 joules of compression or expansion back to the gas. So you're extracting a higher energy than you're providing into the system. So there is a deficit of at least 500 joules, because we know that when we are done with the gas, when we're done with the complete cycle, at the end of the day, the change should be 0. The budget should be 0. The gas should not have anything extra or anything less other than when it started from. So we come down to this equation that what the work done's overall trend has been is that you're extracting more than you're giving. So extraction is more and giving is less. So negative answer is higher and positive answer is lower. So overall, this value becomes actually negative because the overall change is negative. You're extracted energy, you're not giving anything back, or you're giving less back and you're just borrowing more and more energy from it. So since this has to be 0, what should happen to Q? What should we do with Q? So Q should become at least positive, or at least positive enough to become equal to W. Or you can say that since this everything has to become equal to 0, Q minus W, W over there, this becomes W equals to Q. So whatever change in W is missing, whatever deficit of budget is there, must be supplied externally with heat. If you are extracting, for example, if you're extracting 800 joules by letting the gas to expand so that gas does anything, some work for you, you are demanding energy from the system. If you're demanding more energy than you're giving back, then you have to supply that energy from somewhere, and that somewhere we have located, or we have actually discussed that it can only be done by providing more heat during this B to C cycle or during this D to A cycle. This is what we could have done, or at least we are doing. So over here, what you will find in the situation is that he will justify that the work done in C to D is greater than the work done in A to B. This is the first reason where we understand that the negative sign power is actually more than the positive. Hence, it will be compensated, or it can only be compensated by providing Q the heat as thermal energy from the outside. So overall, speaking through A to B to A, again back to A, there would have been an increase in heating effect to compensate for the loss of work done in terms of compression or expansion. Okay, there's just a trade-off. It's just like an accounting problem. You have to give something, you have to get back something. So what we do generally with gases is we deliberately heat them up so that their pressure increases, and then we ask them to do something for us, to lift heavy object, to push back something, and then when that heat is converted into work done, we bring the gas back down again, and then we reheat it again to do the same job again. That's what's actually happening in large pneumatic systems, but that's beside the topic. Anyways, the small sphere is oscillating, so I believe that this question is going to be from SHM. He has given me the equation for velocity, and we know that the velocity equation is also mentioned. The data booklet is omega under root of x naught square minus x square. So I can figure out two things looking at this. This is actually equal to omega, and this is my x naught, which is what he's going to ask you in the next parts. He says find the frequency, no problem. So omega is equal to 9.7, which is equal to 2 pi f, right? So we can simply find the frequency. F equals to 9.7 divided by 2 pi. So when you find this, your F is going to come out as 1.54 hertz. So we're going to write down 1.5. Amplitude is 3.4, and yes, what I've shown you that this is actually x square. So we can pick from the equation x square is equal to 11.6. You take the under root to the other side. We get x naught as simply 3.4 centimeters. So we have successfully shown what the examiner wanted us to show. It says calculate the maximum acceleration. No problem. The acceleration's formula is actually negative omega square x naught. So we have the omega square as well, which is 9.7. So just put 9.7 square exact directly over here. And x naught has been found with the previous part. So if, for example, you were unable to solve this part, you still could have picked up the value from 3.4. So 3.4 into 10 raised to power minus 2. Why am I doing this minus 2? Because I'm dividing this with 100. Because the acceleration is in meters per second square. So I need to convert centimeter into meter. And then don't forget to calculate this properly. After taking the square, you'll forget the square. Please make sure that you don't do that. So the answer is going to be 3.199 meters per second square, which up to two significant figures will be 3.2. This question is a repeated part. It's going to ask you to draw the graph, and the acceleration displacement graph is always going to look like this. So when the acceleration is positive, the displacement will be negative, and the acceleration is negative, displacement will be positive. This is primarily the system of SHM, that acceleration and displacement should be opposite to each other. Or you can look at it in this way, that this is actually a negative gradient graph passing from the origin, or a direct proportionality but with a negative gradient. So we know that this is going to pass. We have found the acceleration, by the way. We know that this is going to be 3.2. We know that the displacement is 3.4, maximum displacement. So let's figure out those coordinates. Let's zoom in and count the number of boxes properly. So this will be 3, and approximately this will be 3.4, I think. The displacement is 3.2. Sorry. Yes, 3.4. The displacement is 3.4. The acceleration is 3.2. So this will be 3.4 up to 3.4. So this will be 3.4 x naught, and the acceleration is actually 3.2. So where is a naught? A naught is already 3.2. Okay. So we don't need to calculate this. So this is going to be a naught up to 3.2. And on the negative side, this will be a naught, but for 3.2. So this will be the center, and this will be the 3.4. So this is going to be somewhere along this line. Yes. So I've calculated I've actually marked the coordinates, right? And then you draw a straight line through them using a ruler, which is going to go like this from the origin back to this point. Okay. This is always going to look like this. Okay, describe without calculation, the interchange between the potential energy and the kinetic energy of the oscillation. How this is actually happening. So we understand that the total energy, which is going to be the sum of kinetic energy and the gravitational potential energy, is actually going to be a constant. And this is what he's asking you about. This is the graph that he's asking you. The one in which you make the kinetic energy graph and the potential energy graph, and you draw a line at the center, and the total energy graph always remains a flat line. This is what he's asking you. Okay, so then we're going to comment about specific points. Of course, when extreme positions, when x is equal to 3.4 centimeters at the extreme position, the kinetic energy will be 0 because it has stopped moving, right? And at x equals to 0, when it passes from the central oscillation, the kinetic energy will be maximum. So these will be enough comments. Okay. All right. Question number 5 is from capacitors. I will teach you this one common point for capacitors that are connected like this. But where do you think you are actually using this idea? You're using this as a power bank for your mobile phones. You charge it from your external charger, and then you use that charged energy to charge your phone. So a power bank actually functions like this. But anyways, let's go ahead. So, okay, capacitor A and B. B has a capacitance of 3 coulombs, and 3 C, and this has a capacitance of C. Switch S is okay. The total initial total charge on QA simply be Q equals to CV. And right now the voltage is of the battery, because when the capacitor is fully charged, it actually gains the voltage of the battery. Because when the voltage of the capacitor and the battery become equal, only then the current will stop flowing. Okay, so this simply goes away as QA being equal to CV. Now, please notice that this QA will help us later, so you have to make sure that you do write down this as QA. The initial energy of EA, and we know that this is half CV square. This will be EA. So this comes out as half CV square. This is just a standard formula for capacitor energy. It says the two-way switch is now moved to position Y. Okay, fine. State and explain what happens to the charge that initially was on capacitor A. So it'll start moving. Okay. So some charge moves to capacitor B, which is this one. But up to what point is it going to move? It will keep transferring. It will keep transferring until both have same voltage. Until both have same voltage, or their voltages become equal. So up till that point, the current will keep flowing. For example, if the switch is moved to this position, the current will keep flowing. Okay, fine, no problem, right? So let's clear this out. He says we have to show that this is the final voltage on the capacitor B, or this will be the voltage after they have done transferring energy. The final potential difference, which means that the energy transfer has stopped. So first we start with this idea that the total charge absorbed by the capacitor A, QA, is what is actually being distributed between QA and QB. So initial total charge is actually going to be distributed between QA plus QB. This is what is actually left with them, right? So this is actually the before case, before injection of charge, and this is actually the after case, because now both of them are going to share the charge, right? So this was CV, right? And the QA is still CVA. Now I'm separating them over here, right? Plus 3 times C, because capacitor B has 3 times the capacitance. And the formula that I'm using is Q equals to CV simply. So I'm replacing every Q with CV and CV. Multiplied with the voltage of B. Now we understand that since everyone will have a final potential difference that is exactly the same as what they have before, or the final potential difference will be same for all of them. So I can see that the voltage of a capacitor B, for example, at the starting stage will be equal to the voltages individually of capacitor A and capacitor B after the charge has passed through. Okay, right? So we get this idea of simply adding them together, right? Since the voltages are same, so this becomes CV equals to 3 plus 1, as the algebra simply suggests. So this will be 4 times CV. Now please notice that what we are after is actually the after case. This is what we are finding, and this is what we already know. So I will make this V the subject of the formula. So capacitance C cancels out. And one more thing, I will make sure that you notice that over here as well. So this is what we're finding out, V. Okay, so let's make that the subject of the formula. This 4 goes over there. So this is V divided by 4 equals to V dash. So today their voltage will be V by 4, and then they would be done exchanging energy. Okay. All right. So now he says to calculate the delta E, change in energy before and after. So we do have the original energy, or the E naught. Original energy was half CV square. For the new case, we need to understand to apply half CV square again. We do have the current voltage, which is V by 4. That's not the problem. The problem is to figure out what's going to be the capacitance. If these two capacitors are finally connected like this, and they have forgotten about, or they have disconnected this previous connection, for example, how are they connected? Are they connected in parallel, or are they connected in series? You see, by the looks of it, this one has to charge this capacitor. Looks like that they are in series, but in truth, they are actually in parallel. Why these capacitors are in parallel? Because the current stops flowing when the voltage becomes equal. And we know that voltage is equal only when any circuit, be that capacitor or resistive, is actually in parallel, right? If this had been in series, then having equal voltage would not have been one of the conditions. They have different capacitances, they have different capacity to store charge, their Q would have been different, but if their voltage is same, that means they are connected in parallel. This is the important point that we need to remember, that in most cases, if you find something like this, one single capacitor across a single capacitor, they are actually connected in parallel. That is why when we know that they're connected in parallel, we are simply going to add their capacitances together. So this will be C plus 3C into V by 4 whole square. So this becomes 1 over 2 into 4C into V by 4 square. When you're done calculating this, this comes out as 1 by 8 CV square, and the original energy was half CV square. If you're trying to find out the change, you simply have to subtract both of them. So we have to subtract half a CV square with 1 over 8 CV square. So what are we left with is 3 by 8 CV square. So this is going to be 3 by 8 CV square. This is the change or decrease in energy of the total energy that was stored in capacitor A. All right. This is important, that they are connected in parallel. That's why it is going to be 4C. Question number 6 is interesting in terms of modern day vehicles, how the charging works, how regenerative braking works. But anyways, we have a disk of radius, vehicle and electromagnetic braking system. Okay, fine. We have uniform magnetic field. It can be switched on and off based on our requirement. Okay, define magnetic flux. And we know that magnetic flux is actually phi equals to BA. Now, since they are being both multiplied, you'll have to use the word product. So it is actually the product of magnetic flux density, because this is what B is, with perpendicular cross-sectional area, because this is the magnetic field. Now let me explain this. If this is a magnetic field, it should be perpendicular to the area. If this is a cross-sectional area, then they should make an angle of 90 degrees amongst each other, right? That's why we have to mention that they are actually perpendicular to each other, or magnetic field and area should be perpendicular to each other. Calculate the magnetic flux through the disk, not a problem. The magnetic flux can be calculated as phi equals to BA. Now in the question, B is already given to us as 0.17 Tesla. We already know that. But the cross-sectional area, since it's a disk and we have the radius of the disk, I will have to use the circular area, which is pi r square. So simply B is 0.17, cross-sectional area is pi, and r square is 0.36 whole square. So when you're done calculating this, this is going to come out as 6.9 into 10 raised to the power minus 2 Webers, WB, right? So this is 6.9 into 10 raised to the power minus 2, capital W small b, Webers. Webers is the unit of flux. It actually counts how many number of lines are actually passing through. Okay. The disk is rotating at 25 revolutions per second. Okay, fine. Now we want to find out the standard, the induced EMF. A very simple, straightforward formula. We have induced EMF being equal to the rate of change of magnetic flux. And if it is with linkage, then of course there will be an N in the, as a part of the equation. But of course, since we are not dealing with a coil, we're dealing with a solid disk, we're only interested in the change in flux. And change in flux can be written down as BA divided by simple T. Okay. The BA has already been calculated as 6.9 into 10 raised to the power minus 2. But notice that this is just one surface area. What do we mean by this statement? He says that it's rotating 25 times in 1 second. So if the disk has started from this point, for example, in its one complete life cycle, it would have encountered this 6.9 into 10 raised to the power minus 2 just once. But in 1 second, it is doing this 25 times, right? But we're only interested to find it one time. So what should we do? By using the ratio method, we can see that this 75 revolutions per second, we only need time for one revolution because this is for only one time. Okay. So one revolution, or we are making at least 25 revolutions. This is revolution and this is time t as 1 second. How much time for just one revolution? So this will come out as 1 divided by 25. Or what you can have done is think on the counteractive side. Think on the other side. We need time for 1 second, right? If this is for 1 second, then in 1 second it is changing the magnetic flux 25 times. Or you could have thought it in this way, that if I am only interested in one revolution, then one revolution time is actually going to be 1 by 25. So no matter what you look at it this from, this 25 is going to come in the numerator and get multiplied. So this is going to come out as 1.7 volts. It's generating 1.7 volts in the disk. Now, this is a good question. He says the axle and the rim are connected into the external circuit. Okay, fine. Use a Lenz's law of electromagnetic induction to determine whether the current in the disk is from rim to axle or from axle to the rim. Explain your reasoning. So if you have to break the disk that is moving, let's say the disk has to be stopped, right? We know the direction of magnetic field is towards the right side. That's not a problem, right? But if I want to do that, then I should apply a force in the opposite direction. This should be the force. And this is the direction of magnetic field. So I am going to reverse engineer this question in this regard, that the force required to stop this should be applied in the opposite direction. Why? Because this moment, this tire is actually rotating in this direction as represented by this arrow. Okay, so if the disk is rotating this way, I should apply a braking force in this way. When you use the Fleming's left hand rule, you realize that your first finger should be aligned in this direction, right? And your second, this is going to be your finger, right? Your thumb should be aligned like this, right? And when you've done that, when you open up your second finger, it is going to open up in this direction. The second finger opens up like this. So the current from all edges is actually going to move from rim to the axle. The current is moving from rim to the axle. So the current is moving from rim to the axle. And how we have done that? Because we know that the magnetic field is cutting the disk. And the disk, after getting cut through the magnetic field, is going to experience an induced EMF, which you've just calculated. The value is 1.7. This induced EMF will cause a flow of induced current, right? And that induced current is actually in the direction of from rim to axle. All right, so we understand this question at least, what he's trying to say in the marking scheme. Question number 7, question from diodes, rectification, AC electricity. He says draw the rest of the diode, but let's see for the first. So type of rectification produced. Since this is a 4-diode model, this will actually be full wave rectification. If you go back to the video uploaded on my channel about AC electricity, you will also see that there is a full bridge rectifier with 2 diodes. So don't be fooled by that. Okay, anyways, if I have to make the diode in this way, or if I have to arrange the diodes to complete this diagram, first we need to make sure that the current actually flows in the same direction. So if the current is actually coming from this point, let's say, that means that the current is actually going like this and then like this. Then of course it cannot go back towards this side to go from this resistor. It can't go like this. It could have 2 choices. It could have gone, let's say, in this way, for example. But then again, if it could go this way, then where will the source get involved? How the electrons are going to be pushed around? So this is what it looks like. So the next path it is going to have, it should be like this, then like this, and then like this. So one of the loop is complete, which makes sure that the current should be in this direction, or at least the shape of the diode should be in this direction. We figured that out. Okay. Now let's go on for the rest of the cycle. You see, if I consider this, let's say, if I consider this to be the positive current through the supply, then this should be the negative current in the opposite direction, of course, right? Now, if the negative current has existed or exists in this way, I cannot, or at least this current cannot go towards this side because the diode is going to block it. So the only choice that I have is to make sure that the current flows in this direction. So this diode has also been figured out to look like this. Okay, let's move on. So when this current has been allowed to flow through, of course, it cannot go back to the source. It cannot go through this resistor again, or this circuit loop again. Okay, it cannot go back to the supply again without passing through the resistor. That will be a short circuit. Okay, so then in the previous cycle, we ensured that by this diode and by this diode, the current was flowing in this direction. So let's see if we can make sure about this one as well. So the current flows in this direction, in this direction, in this direction, and then it has 2 choices. Okay, so it will flow through this branch. Now, why is it not flowing through this branch? Why cannot it go back from this path? The diode actually matches. You see, there is a problem. The problem is that when the negative current was initiated, 220 volts were existing at this point. If we are considering VABDA, for example, then this is 220 and this is negative 220. So the electron has a 220 volts at this point. When the electron passes through the resistor, it comes to this node, it approximately has 0 volts. It has nothing to give, right? Or let's say 5 volts. Let's say it has very little amount of energy, just enough to make the next diode forward biased. Now this 5 volt electron also reaches at this point. Why doesn't it go towards this side? Because this diode is reverse biased. The voltage at the back end is less than the voltage at the front. So the potential gradient is actually set like this, and the diode cannot allow the current to flow backwards, which is why the current will not flow through this. We are just using arrows to check the direction. Okay, so I have to allow this current to go back to the supply. Okay, so the diode that is going to make do of this situation is going to look like this. So all the diodes are pointing towards the left side. And let me show you an animation for this to further solidify how this actually looks like to you. These are 4 diodes, right, connected in this manner. Just a moment, let me show this animation separately. Okay, so I hope that you can see this on the screen right now. Notice how the diodes are activating and deactivating at the same time. And notice how the current is actually always flowing in the constant same direction through the resistor. You can rewind this video as many times as you want to fully understand this, how the diodes are actually functioning. And you can also see the direction of current changing through the supply as well, because of AC supply. Okay, so I hope that we understand this now. All right, we've done that successfully. He has given us a graph. He says, draw an arrow to show the direction of current. So we can see that this is the direction of current of current. He's given us the voltage of V in, voltage in of the AC supply, which is actually drawn at this point. This is what he's asking us. And this is the V out. You see, this is what the V out is going to be. So it's a very standard graph, no problem in that. The graph is actually full wave rectification. So this is going to actually look like this. Just a moment. You see, if I go back, I have 0.5 T as well at a negative voltage. So these points of crossover are actually going to become where the voltage is going to be 0. So first let's plot them. Okay, let's first plot them at least. So we have the center approximately 0. This is 0. This is 0. This is 0. And wherever I see them to have either a positive or a negative value, I will make a high voltage sign at that point. So at the very beginning, at 0.5, at this point, at this point, and at this point. At 0.5 T, at 1 T I see, at 0.5 T I see a negative value, at 1 T I see a positive value, 1.5 see a negative value. But since now they have been converted into full wave rectification, everything will become positive now. As we remember that the full wave rectification output is like this, which is not smoothed out by a capacitor. So this is what the graph is going to look like. Of course, I cannot draw them properly, but you can draw this with lead pencil much more precisely on the notebook. This is what it's going to look like. Okay, all right. So he says the power dissipated in the resistor is P. Okay, fine. Sketch the variation of P between T0 and T2. Now this is going to be a bit tricky. You see, we have to calculate power, we have the formula of I RMS into V RMS. Now, but if we go to the exact, this is actually the mean power, the average, okay? And this is what we actually use in physics as well, because instantaneous power is going to become a problem. What is instantaneous power? You see, if we look at the graph of voltage, let's say this is a voltage graph with a function of V naught cos of omega t. We have a graph of current as well, which is going to be, let's say, a sinusoidal graph of I equals to I naught cos of omega. By the way, this is a sine graph. Let me rephrase this. These are actually a sine graph, right? Cos graph looks different. So anyways, this is a sine of omega t. This is also sine of omega t. Now, if I choose a certain time of my choice, let's say this time t and this is time t for both of them, and if I wanted to find out the instantaneous power, let's say P instantaneous, then that would have been I and V, which would have been I naught, right? I naught with a function of sine, I naught sine of omega t of my choice, and then V would have been V naught sine omega t. When I open this up, it becomes I naught V naught sine square of omega t. So this is the instantaneous power. And if I'm looking for peak power, I realize that the peak power will actually be the V peak and I peak, right? And luckily, we have also devised a method for this, that the peak power, if divided by 2, is actually equal to the RMS power, right? This is what we already know. And how do we get this? If you, let's say, to find PRMS, I've also done this in the proof as well. We have IRMS multiplied by VRMS, which is equal to I peak multiplied by V peak, but respective under root 2 under root 2. So this becomes I naught, which is the peak current, peak voltage, multiplied becomes peak power divided by under root 2 multiplied by under root 2 gives you 2 divided by 2. So the RMS power or the average power is actually equal to the peak power divided by 2. But of course, we know that the peak power is not what always flows, because that only happens momentarily at only just 2 instants, right? So it's infeasible. It's not feasible for us to calculate this again and again. So what we are trying to understand over here is that this power function, which actually is going to look like a sine square, or if you were using a cos function, this would have looked like a cos square function, because everything has become positive now. What's the difference? What's the problem? The problem is that the voltage graph has sharp peaks like this one. But just because of mathematics, we realize that the graph of cos square is going to look a bit smoother. This is the difference. So the graph is going to look like this. Exactly the same. Let me draw that. It's exactly the same as voltage, right? It's exactly going to be like this. So let me draw the voltage graph again. It's exactly like the voltage graph, but the only difference is going to be about this edge smoothness, which is a mathematics problem, not a physics problem. What will happen now? So this graph is going to go like this, smoothly move over like this, then smoothly move over like this, and so on and so forth. Exactly the same graph, but with smoother falling and smoother rising up again. So I'm going to erase this green line now, right? This is what's not your answer, and red line is your answer. So please add one more thing in your graphical at least knowledge, at least, that the cos square function, or at least the power graphs, or the power graph is actually going to be made like this. The sharp edge will be for voltage and current, but the smooth edge and smooth curve will be for the power, because it will have a cos square or a sine square function. Okay, so we move on to the next question. He says, a very stupid question. I understand that. I accept that there's no point asking this question, but anyways, let's move on. With the reason how root mean square V out compares with the V in, the value of V out or V in will exactly be the same. The value will be the same. Why? Because how does the root mean square work? You see, the V in was actually like this. The root mean square, what it tries to do is tries to find out the total cross-sectional area, or the area under the graph. First, it takes the square so that everything becomes positive. Then he takes the under root to balance out the square it took in the first place. So now the graph becomes like this. And then he finds out the total area under the graph, which is this one, and divide that area with the time period, or the time where it is supposed to be spread out. So that is how they find out the RMS, or the standard value of the graph. So now there is a value of constant area spread out on a certain time period t. So we did this with V in. Is there any point doing this with V out? No, V out is already a square, or is already a positive graph. It's already like this. If you take a square of this, it makes the peaks larger, and then you take the under root of them to bring them back again. So when you do that situation of mathematical operation as well, it does not change the effect. There's no matter taking the square of 2, making it 4, and then taking the under root to make it 2. It doesn't matter, because everything is still positive. It's on the positive axis. But yes, dividing this total area with time t, or the total time to spread out with a constant value so that the area becomes constant, of course, that will be required. But if you do that for the V out, which has been a rectified output, they both will give you the same answer, because RMS is what we are trying to do over here. So I've explained it visually, at least, what RMS actually looks like. So they're both exactly the same. Okay. All right. So we move on to question number 8. This is from quantum physics, energy levels, hydrogen, so on and so forth. So it says that there are 4 energy levels of an electron in isolated atom system. Okay, fine. One thing that is misleading in this question is this. Let me erase this figure 8.41. What is missing in this graph that actually misleads us? Where is the ground zero? Where is the n equal to 0? When you get to the nucleus itself. Now this is the first electron shell. This is the second electron shell. This is the third one. And this is the fourth one. This is what these energy levels mean, right? So this n, or not showing this n equals to 0, is actually what actually, causes some misleading for the last question. But anyways, let's see. He says that the corresponding to emission transition lines from N3 to N1 and N4 to N1. So we have N3 to N1 and N4 to N1. There will not be a lot of difference between them, but first we need to understand which one is going to be which one. This is important. But anyways, okay, so shows the line of emission spectrum. Okay, corresponding T. Fine. Explain with reference to photons why there is a single line frequency of electromagnetic radiation corresponding. Now, this is a classic property of photoelectric emission and the quantum behavior. See? So, we know that the energy of a photon is represented by its respective frequency. So, this is the first fact that you have to state. That frequency corresponds to the photon energy. And since the jump is discrete, it's definite. The photon energy is discrete and definite. It's not a range of values, right? So the transition is discrete, definite between two levels. Releasing a photon of a specific and a certain frequency, right? Okay, because we know that it's going to be something like this, that change in energy level E2 minus E1 is actually going to be equal to HF. Okay. On figure 8.1, draw the line that corresponds to transition from N2 to 1 and then N3 to 2 as B. So let's move on to N2 to 1. What's going to look like? So N2 to 1 is looking like this. Okay. So this is going to be the energy level of N2 minus the energy level of N1 equals to H. Now, since we are dealing with the frequency, that's going to be F directly. Okay. So he says that the first change is represented as A. Now, of course, these lines which were represented over here are spread out for N3 to 1 and N4 to 1. Okay. So this line looks like it fell from N4 to 1, and this line looks like it fell from N3 to 1. Why? Because if the change in energy is high, the frequency will also be high. So since this is increasing frequency, right? So this would have been a larger change. This would have been a smaller change. That's why this is the prediction before starting the question. So I believe that the next answers that we're going to have, this 2 to 1, it cannot be greater than 3 to 1. It cannot be greater than this change. So it's going to be somewhere along this side because its frequency will be lower than that. Because this change, which is 3 to 1, has a higher delta E. If the delta E is higher, the frequency will be higher. So since the delta E or the change is lower, the frequency will be lower than the comparison to N3 to 1. So this is going to be the fall from N3 to 1. Sorry, 2 to 1. This should be N2 to 1. Let me rephrase this. Yes, this is the fall from N2 to 1, which he has said to label as A. So I will label this as A. Then he says to label the line B from N3 to 2. N3 to 2, what does that look like? So N3 to 2, so N3 to 2 has a smaller change in energy, so its frequency will be even smaller than this. So it should fall back a little bit more, right? It should be somewhere along this line. So this should be B. Okay. And please notice that what we are comparing right now, we're comparing 2 to 1 and 3 to 2. So 2 to 1, which is going to be blue line, right? Let me erase the rest of them. This is the line that is being compared with this one. Now, visually speaking, at least, we can see that this change is somewhat half of this change, or at least 2.5 times or 3 times. So if the change is lower as compared to this, then the frequency will be lower but proportional. So just make sure that this B is not drawn too close to A. That will be incorrect. Although conceptually right that it's going to be behind B, behind A, for example, but at least conceptually wrong. Why? Because the change in energy is higher. So in this case, the change in energy was smaller. And in this case, the change in energy is higher. So it should be much, much greater further away from those two reference lines. Okay. So just make sure of that. So we've done these parts as well. We move to part number C. He says in part C, we have all the things are in terms of variables. Okay, fine. Tell me the expression in terms of FA, FB, E1, H, E3 of the energy level N3. An expression in terms of, okay, so what would be E3? So E3, which is, let me erase this. So where is E3? You see, this is where the misleading ideas come from. N0 was not given to us. So let's draw this N0. So to go from N0 to N3, this is actually E3, or this is the energy E3. And then we have E1. To go from N0 to N1 is actually E1. And we have to go up to N3. So what are the chances that we have? So we could have gone through this transition, which is from 1 to 2, and then we could have gone through 2 to 3. These are the transitions that we already have. And do we have the representatives on the graph? I think so, we do have. So this was 2 to 1 or 1 to 2. This was FA. This is what he labeled or asked us to label. And B was from 3 to 2. So this was from N3 to 2. So N2 to 3 back up again, this could be the frequency B. Okay, so we can represent E3 or the change of E3 in these representations. So what we need to do, we need to just add them together. So this would have been HFB plus HFA plus the energy level required to go from 0 to 1. If you add all of them together, you will find the energy to be equal to E3. So this is what that equation or the system was going to look like. This is what the problem is. So E3 was equal to the energy level 1 because of course our reference is 0. So to go from N0 to N3 and to go from N0 to N1 plus the HFA plus the HFB jump. Okay. So you can simply write this down like this one. Or, of course, another implementation would be something like this, that E3 minus E1 is equal to HFA plus HFB, which is plausible, of course, because if you want to know the difference, for example, if I take the difference of them, let's say from 3 to 1, FA and FB do fall in this category if I take a difference of this E1 minus E3. If I minus or if I subtract E3 from E1, the only height or the only transition left is of HFB and HFA. That is also acceptable. You can also think like that. But eventually, even then, E1 has to go to their side and get added together. So we end up with the same result. Okay. So this would have been E1 plus H into FA plus FB, because Planck constant is common for both of them. So in the marking scheme is just simply added them together like this. No need to worry. Then we have mass defect. Mass, if you can memorize the definition of the book or the marking scheme as well, it is actually the difference of mass of what? Of nucleons when they are inside the nucleus. When they are inside the nucleus and when they are separated to infinity or infinite distance. Why do we have to say that? You see, In the nucleus, they are very tightly bound together. Okay. And when we provide them with the binding energy, if we break them apart into nucleons, we have to mention this, that they are separated to infinite distance, because now we say that they cannot be influenced by any fusion, and they cannot be brought together. So wherever they were, whatever space they were confined in was much smaller in comparison to where they are now. That's why we say that this distance is infinite in comparison to what this distance would have been. That's the only understanding of this. Okay. All right. So masses are given. We are given with the particles. We also have an equation. We have an equation before the system, and we have an equation after the system. So he says, state the name of the particle X, and very simply we can see that this looks like a neutron, which is N10. So to balance the equation, of course, this is the neutron. Okay. It says show that the energy released when one nucleus of H42 is formed with the fusion reaction of this much. So these are fusing together to make this. And we have H42. Okay. Their respective masses are given, right? But this is not their mass, this is actually their mass defect. What is the meaning of mass defect? That in this part, in this system, if we had a nucleus of helium-42 and we had compared it with, for example, another system in which we had 2 protons and 2 neutrons, right? Then this side would have been heavier and this side would have been lighter. And the difference between this M2 and M1 is actually given to you as delta M over here. And same is for this one, same is for this one. So everything that is given to you over here is actually a mass defect of their respective nucleons broken apart. So you can use the equation E equals to mc square for every single one of them to actually figure out how much energy would have been required to actually make them or actually break them apart, or how much energy will they release in terms of a fusion reaction if we were able to do that. Okay, so this is the idea and concept behind it. So let's do that. He says that this energy is released, so we need to use the equation E equals to mc square, but not any mc square, the change in mass square. To find out the change in mass, or the delta M, we need to subtract the masses given to us. So 2 of them are in the products and 1 of them is in the reactant. Sorry, these 2 are in the products, and this one is in the, this one is reactant, and these are in the product, right? So let's do that. So let's take the difference of both of them. So this 0.03077. Now take full values, of course. If he has given you to this extreme, you should also take them to this extreme. So 0.03037 minus both of the reactants added together, 0.002388, plus this was actually the mass of H21 and this is actually H31. So plus 0.009105. Okay. This is the change in mass of the whole situation multiplied by c squared, plus this is actually the atomic mass unit. This is actually in terms of U, and we know that from U, 1 U is actually equal to 1.66 into 10 to the power minus 27 kg. This value is also given in the data booklet as well. So let's convert this into kg as 1.66 into 10 to the power minus 27, plus multiply this with 3 into 10 to the power 8 whole square. When you do that, of course, this will not remain a change of mass up to this point. And this is just delta M, and this is c square. If you multiply all of this, you will get 2.8 into 10 raised to the power minus 12 joules, which he wanted us to show. If he wanted you to convert this into electron volts, what you would have done as an extra step, divide this with 1.6 into 10 raised to the power minus 9 joules per electron volt. Joule cancel out, and your unit would have become into electron volts or mega electron volts. C part. He says the star in B has a radius. Okay, so this was a star actually, a fusion reaction taking place inside the star. Okay, fine. Has a radius this much, luminosity of this much, the energy released from H2 away from the star has been released in the formation of, okay, fine. Determine the mass of H4 produced per unit time by the fusion process. No problem. So we have the general formula for power, that is power equals to energy divided by time. Power was actually given to you, okay, and time is what we are supposed to find out. So we have this much amount of energy released from just one fusion process, right? So we release 2.8 minus 12 from one process. The star is actually producing this much power, so we can find out the number of atoms who are actually doing this. So we have to produce a power of 1.4 into 10 raised to the power 28 equals to who is providing this energy. One atom is producing this energy as 2.8 into 10 raised to the power minus 12 joules in 1 second as time, right? So if I can find out the T, or the number of atoms at least released per unit time, right? So this would have been simply T over there and bringing this over there. So this would have been the number of atoms per unit time would have been 5 into 10 raised to the power 39 atoms, or at least reactions. So this many reactions should take place. When multiplied with this one, will produce this luminosity, will produce this much power. Okay, it's just a ratio method, by the way. Okay, if this one reaction produces this much, then X should produce this much. We might not have to use this P is equal to E by T as well. This could have been done by ratio method. So we know that the mass of one helium-42 is actually 4 multiplied by 1.66 into 10 to the power minus 27 kg. We know this, right? So this will be the mass calculated as 6.64 into 10 to the power minus 27 kg per atom. And we have these many atoms inside that star. Okay, so this is a very huge number going to be. So if we multiply this with this, the number of atoms, and all of this is happening in 1 second because this is joules per second, right? So that would have been 6.64 into 10 raised to the power minus 27 kg per atom multiplied with the 5 into 10 raised to the power 39 atoms in 1 second have been produced. So atom cancels out, and simply a straightforward ratio method, we get 3.32 into 10 raised to the power 13 kg per second are being produced per unit time, which is a very huge number. The surface temperature of the star, no problem. We have the Stefan-Boltzmann law, which is L equals to 4 pi sigma square, sorry, sigma simple R square T raised to the power 4. So we have luminosity, we have 4 pi and sigma, we have the radius as well. We need to find the temperature. So let us place the value. So luminosity was given to us as 1.4 into 10 raised to the power 28. 4 is the constant, pi is a constant, sigma is 5.67 into 10 raised to the power minus 8 as given in the data booklet. Radius is 2.3 into 10 raised to the power 9 whole square, and T has been raised to the power 4. Please don't forget to take the fourth root of the answer. Your answer should be 7800 Kelvin, which is going to be mentioned here. We move on to the last question, which is question number 10, X-ray medical physics. Okay, let's see. He says, okay, fine. Potential difference, a potential target. Okay, fine. Charged particles are accelerated towards the metal plate by applying a potential difference. What are those particles? So we are actually accelerating electrons to hit a metal target. Explain how X-rays are produced at the metal target. So they basically slow down. So electrons decelerate upon metal interaction, and this sudden deceleration causes a kinetic energy loss. They slow down, and as a result, when they're slowing down, their energy is converted into a gamma or X-ray photon. This is converted to an X-ray photon, which is then received on the outside. There is a name of this process as well, although not a part of your course, but you can go online and see how X-rays are produced, and they will tell you the name of the process by which this is produced. The electrons actually decelerate, they slow down, and since this sudden deceleration is accompanied by a release of X-ray photon. The maximum wavelength produced by 5.8 kilovolts. Now the formula that we're going to use over here is important. You already know this, but the implementation is important. So work done is equal to QV. We got this from voltage is equal to work done by charge. So that energy has to come from somewhere. So that energy is coming from or converting into a photon, which is hc by lambda. So let's equate both of them. So we get QV equals to hc by lambda. So voltage is given to us as 5.8. So let's put that over here. The charge of an electron is known, 1.6 minus 19. Voltage is known, which is 5.8 into 10 raised to the power 3 kilovolts. H is 6.60 Planck constant into 10 raised to the power minus 34. C is 3 into 10 raised to the power 8. And this whole being divided by lambda. So let's replace their values. And algebraically speaking, lambda is going to come out as 2.14. 2.14 into 10 raised to the power minus 10. So this becomes 2.14 into 10 raised to the power minus 10. This question is about attenuation, loss of power, being absorbed, so on and so forth. It says that the attenuation constant is 1.4, the thickness is 2.8, is absorbed, right? So let's say that this is the tissue, and the thickness of the tissue is 2.8 centimeters. The introduction of X-ray that you've introduced is, let's say, at 100%. So this is 100%, or you can say this is standard I naught. What are you going to get as the output? This is your standard I. He says what is absorbed. What we get is what is on the output. So I is equal to I naught e raised to power minus mu x. This actually tells you how much are you going to get back. So if I can get what is going to come back to me, or what is being received, I can figure out how much is actually being absorbed or lost between the sheet of this tissue. So let's replace I naught and e raised to power negative of 1.4 into 2.8. Now, since everything is in centimeter and centimeter, I don't have to convert anything into any other values. This answer comes out to be a very small answer, which is going to be I naught into 0.020, which roughly narrows down to 2% of I naught. What does that mean? It means that if I am sending 100% of X-ray, I'm only getting back 2% on the output. So how much has been absorbed? 98% has been absorbed within this tissue. So you will find this percentage to be 98% of I naught is absorbed, and only 2% was received after it passed through the tissue. Okay.